All right, so to wrap up section 14.2, I want to return to this example. We had started working through this before, and I had mixed this one up with a different example that I was hoping to do, and the one that I was thinking of would have failed to have the same limit as these three paths up here with a different choice of with a different choice of a path, and that's not what we ended up with here. This one, the limit actually does exist, and if you notice, all of these different paths where xy is approaching 0, 0 keep giving us 0. So if the limit exists, it has to be 0 because all of those paths would have to go to that limit. But again, like we've said before, you can't check every possible path, every possible way of approaching the origin because there's an infinite number of those. You just can't go and check an infinite list of possibilities. So instead, we need to approach this a different way. Now we've seen, using the squeeze theorem and using some algebra to simplify the function that we're taking the limit of. But in this case, what I want to do is use the actual definition of a limit of a two-variable function. And so just as a reminder, here's that definition again. The limit as xy approaches ab of some function f of xy is equal to this number L. If this condition down here is true, for every positive number epsilon, you can find a positive number delta. And I want to mention something about this too. This delta is meant to depend on this epsilon. Notice the words for every here. That means we kind of think of epsilon as some arbitrary positive number. It can be literally any positive number. But once you've identified a positive number for epsilon, you would then go and find a corresponding number delta that matches with that, which makes this statement down here true. So what that means is that different choices of epsilon may require different choices of delta to make this work. And that for that reason, delta is oftentimes represented as some function of epsilon. So with that said, this is really the important part down here. For any xy in the domain of our function, if the distance between xy and ab, that's what this expression is here, is less than that delta that we would have identified here, but greater than 0, meaning that the distance is positive instead of just xy and ab being the same number, then f of xy minus L, or the distance between f of xy and L for that choice of x and y, is less than epsilon. When we do these epsilon delta proofs, we typically want to start here and work our way backwards to identify a delta, and then we restate everything in a way that satisfies this condition. So again, starting here, we have the function that we want to take the limit of, and we have a limit that we've identified, 0 in our case, if this limit does in fact exist. So here's what we are trying to show. We want to show that the limit as xy approaches 0, 0 of x y to the fourth over x to the fourth plus y to the fourth is equal to 0. Again, the evidence suggests that if this limit exists, then it would have to be 0. Now, before trying to prove this, let's actually write out what it is we're trying to do. We want to show that for any epsilon greater than 0, there exists another positive number, delta, greater than 0, such that if this is true, now again, remember the statement of our definition says x minus a, y minus b, but a and b are the coordinates of the point that xy is approaching. And in our case, we're approaching 0, 0. So that would look like x minus 0, y minus 0, both squared. And that's really just the same thing as this, x squared plus y squared. So we want to show that for any epsilon greater than 0, there exists a delta greater than 0 such that if, I forgot my if there, if this is true, then, now think of this next part. F of x is this function right here. X, y to the fourth over x to the fourth plus y to the fourth minus our limit, which is just 0, is less than epsilon. That's what we want to show. Okay? Now, like I said, we generally start here. There's that less than epsilon. Kind of zoom out a little bit. And we work our way backwards to try and identify the delta that we would need. And that delta is going to be represented in terms of epsilon. So let's start here. The minus 0 is actually unnecessary, so I can just do this. Xy to the fourth over x to the fourth plus y to the fourth. We want that to be less than epsilon. Okay? Now this absolute value, we can actually do a little bit with that. Notice the denominator is it's already guaranteed to be positive because we're raising both x and y to even powers and then adding them. So this would have to be a positive number. This implies that the absolute value is not necessary down here. Same thing here. Y to the fourth power is going to be non-negative no matter what we plug in for y. So there's no need to have the y to the fourth power within absolute value bars. This is the same thing as just writing this. That x is the only thing that could potentially be negative. That's less than epsilon. Okay? Now, I can bring that absolute value of x out to the front here, and that leaves me with y to the fourth over x to the fourth plus y to the fourth. Okay? Now this thing is what we want to be less than epsilon, and I want to focus primarily on this part right here. That y to the fourth over x to the fourth plus y to the fourth, we know that that's going to be a positive number, or non-negative. Y could be 0 technically. But beyond that, we can also say with certainty that this quantity is less than or equal to 1. And why do I know that? Well, look at my numerator. My numerator is some non-negative number, and that exact same non-negative number is showing up right down here in the denominator, and then I'm adding more to it. So unless x is equal to 0, in which case y to the fourth over y to the fourth would equal 1, unless that's the case, this will be a positive number, giving me a larger positive denominator than my positive numerator, giving me a number that's less than 1. So what we're going to do is think of this as just being 1, and we really want the absolute value of x to be less than epsilon, because if that's true, then we have this. Absolute value of x, y to the fourth over x to the fourth plus y to the fourth would be less than or equal to the absolute value of x times 1, based on that argument that we just had. You don't need to write that. And then this would be less than epsilon. So if we can get this absolute value of x to be less than epsilon, then this will be less than epsilon automatically. Okay? But remember, the goal here is to find a delta. And now this is the thing that I want to start working with to try and get there. Well, notice that the absolute value of x is the same thing as the square root of x squared. We know that from algebra. These two things are identical to each other for any value of x. But this number, the square root of x squared, is less than or equal to the square root of x squared plus y squared. And again, the reason for that is because I have my x squared showing up here and then again here, but on the right-hand side, I'm adding some non-negative number to it, which means this number can only be bigger than this, or if y is equal to 0, exactly equal to it. But this will never be less than what's on the left-hand side. And if you notice, my reason for writing this is because that is part of the inequality where this delta shows up. So that delta is what I want this thing to be less than. But again, I want to be able to retrace my steps and end up back here. So what I'm going to do is set my delta equal to epsilon. Set delta equal to epsilon. And then when I work these steps backwards, I'll get exactly what I want in order to show that this limit exists. So now this is essentially like the work in getting to our choice of delta. Now that I've done that, I'm going to write this out in the form of like a epsilon delta proof, or delta epsilon proof. So I'm going to say let epsilon be greater than 0. And then what we're going to do is say, suppose this is true. And suppose 0 is less than the square root of x squared plus y squared, which is less than delta, which we're going to set equal to epsilon. Okay, you can actually leave the delta off completely and just work entirely in terms of epsilon now, but it's okay to write it this way too. Then, how do we rewrite everything so that we're getting this statement here? Well, I basically retrace everything. So starting with this side, the absolute value of x y to the fourth over x to the fourth plus y to the fourth minus 0, based on all the work that we did up here, is, we know what we can simplify it to this. So this is equal to the absolute value of x y to the fourth over x to the fourth plus y to the fourth. And as we showed, that would be less than or equal to the absolute value of x. And again, that's because that this part of my expression is going to be less than or equal to 1. That's less than or equal to x. This is equal to the square root of x squared, which is guaranteed to be less than or equal to x squared plus y squared under a square root sign. Now this, we have an assumption about this that we made at the beginning of this little proof, and that's that this thing is less than epsilon, because delta is equal to epsilon. And if you notice, that establishes what we wanted to show, that this expression, the absolute value of our function minus 0, is less than epsilon. That's what we have right here. Through this chain of inequalities, we eventually get that this thing is less than epsilon. So therefore, little dot dot dot, that means therefore the limit as xy approaches 0, 0 of xy to the fourth over x to the fourth plus y to the fourth is equal to 0. You're not really going to be asked to do these epsilon delta proofs much at all in this section, because they are notoriously difficult at this level. So, you know, most of the time you're going to be able to use some other approach to evaluate a limit, but I'm glad that this one came up, because it shows you what it looks like if you do need to find a limit using that definition directly. But that's going to wrap it up for 14.2.